Pattern made on the paper is displacement time curve for any oscillating system. Now let us try to make a wave like pattern same as what we have observed in the graphic calculator. For that we are using Desmos. F of x is equal to sine x gives you a wave like pattern. If I add omega t plus phi to the equation, where omega can be written as 2 pi upon t. I'm putting t is equal to x because time is coinciding with the x axis. Let's change phi. If I increase phi, the wave like pattern moves towards the left. If I decrease phi, the wave like pattern moves towards the right. Over here, as I said, I'm putting omega or w as 2 pi upon t because that is angular frequency. That is how much time it takes to cover 2 pi radians divided by the time period, that is capital T. As I add an argument a to the equation, by changing a we can see amplitude changing, and by changing the t we can see the frequency changing. So you can see here that the wave squeezes or expands as I change t, and the amplitude of the wave increases as I change a. As you can know that the sine function can only have a maximum value of 1 and minus 1. So changing a will change the amplitude of the whole wave-like function. Now to describe a superposition of the two wave, I'm gonna copy the first equation and name it as g of x. For this equation, second equation, I want it to move opposite to what the first wave was moving. So instead of writing omega t plus phi, I'm writing omega t minus phi. As I move the slider of phi, you can see the black and the green waves represented by each equation are moving in opposite direction. The green wave moves towards the left and the black wave moves towards the right when phi increases. And let's see what will happen if I try to define a superposition of the two waves by defining a new function in a while. The new function, I'm gonna choose s of x, that is sum of the other two waves f of x and g of x. That means superposition of the instantaneous displacement of each wave function or wave equations. So as soon as I define it, a new superposition of a new wave appears in red, that is superposition of the two. And when now I press a play button to phi, then you can see that the red curve is actually representing a standing wave. Although the two constituent waves are moving in opposite directions individually, but the superposition of the two waves doesn't seem to move. In here you can see the nodes and antinodes represented by the points highlighted, and also you can observe that the maximum amplitude of this superposition of the waves is 2, that is sum of the individual amplitudes, that is 1 for both of them. Now in this part I want to show you a demonstration using the graphic calculator of how a beat is formed. We know a beat is formed when the two waves that are superposing with each other differ from each other by a slight amount. To represent this slight amount, I'm gonna write the frequency omega plus a for the second wave g of x, and this a, if I vary from 0 to 10, you will see that the pattern of superposition is more like a beat. It's not clearly observable at this zoom level, but let's hold on for a second and see the beat forming when we zoom out a little bit. As you can see now, the beats are clearly visible, and these beats seem to be traveling. What happens in a beat is when two waves of almost similar frequency superpose with each other, a beat is formed. This is similar to the CRO demonstration I have shared earlier, and this is it for today.